Okay class, this is a lecture on representing enthalpy change. This video itself is not mandatory or required to watch. It's just a few students have requested that I make the videos for the days that I'm not at school. So if you want, here it is. This is section 5.3 in your Nelson textbook. Okay, so today we're going to look at 4 different ways to communicate enthalpy changes. So the very first one, including energy in the equation. Now we've seen a few examples of this already. Here we have methanol burning. So we put, it's an exothermic reaction. So we say energy is a product. So we include energy in the chemical reaction on the product side. The second method is to state delta H separately. So here we have our chemical reaction, CH3OH, we're burning with oxygen, and then on another line or away from the equation or away from the reaction, we're stating the delta H value separately. Now here you notice we have this negative sign because it is an exothermic reaction. When you're stating it separately, you have to put the negative sign for an exothermic reaction. When you're putting it just inside the equation, you get rid of that, you just put a plus sign because we're placing it either as a product or a reactant. The third way, state molar enthalpy of a specific reaction. So this is something that's a bit new. Here we have delta H combustion. So we're specifying what type of reaction we have, and we're just stating what the value is. So for 1 mole of CH3OH or 1 mole of methanol, we're burning or we're releasing 726 kilojoules of energy. And finally, the fourth one, this is something completely new that we've never seen before. Drawing chemical potential energy diagrams. It looks something like this. I'll go into more detail as the video goes along. So for the first reaction, now again, for all these reactions, just assume that reactions occur at SATP, so standard temperature and pressure. It just gets rid of unnecessary details. So if the reaction is endothermic, include energy as a reactant. So here we have it inside the reaction on the reactant side. And if it's exothermic, you place it as a product. So here we have for this reaction, energy is a product. Pretty straightforward. For the second method, what we're going to do is balance the chemical equation first, and then we can modify delta H based on the number of moles. So here we have an equation, half a mole of CO. So if we're given something like this on a test, half a mole of CO doesn't exist. And if we're saying that delta H value for half a mole of CO is negative 64 kilojoules, when we balance the equation, so in essence we're doubling this value right here to get 1 mole, we're going to have to double the delta H value as well, so we end up with negative 128 kilojoules of energy. Method 3, here we're using SATP, so specifically we're stating everything that was done at for this reaction was done at standard pressure and standard temperature. So that's signified by this little degree sign right here. If you find a delta H value that's stated and it doesn't have the degree sign, that means it was done at a temperature or a pressure that's different from the standard. If you want to see a few examples of these, you can find it on page 316, table number 1. Now standards can be stated for any kind of reaction. It doesn't have to be a combustion reaction. Just state what kind of specific reaction it is. So this X subscript right here, you're going to replace it with the type of reaction. So we could say delta H of combustion, delta H of neutralization, delta H of formation. Just specify what kind of reaction it is. So here we have our reaction. This is a formation reaction, formation of methanol. So we're going to state specifically delta H with a degree sign and then subscript formation of methanol. So 1 mole of methanol is negative 128 kilojoules. Okay, this method, it gives you a lot of information in one line. It just has to be done correctly. So be mindful of all of this information. And the last method, visually communicating data. So here we're making graphs just to show if it's exo or endothermic. Now this is based on the principle that energy is stored or released in chemical bonds. Okay, if we have an endothermic reaction, we're saying that energy was absorbed by the bonds, and if you have an exothermic reaction, we're saying the bonds were broken and energy was released. So on the graph, our vertical axis will be potential energy and our horizontal axis will be reaction progress. So for this example right here, so the burning of methanol, so combustion reaction, we start off at high energy. Now there's no numbers on this axis right here for energy, it's just arbitrary. We're just showing that we start off at high energy. So I could have put the bar over here too, it doesn't matter. As a reaction proceeds, so reaction progress goes ahead, as we start burning, we're losing that energy in the bonds. So these carbon-hydrogen bonds or carbon-oxygen bonds, high energy, but we're losing them now. as it's being burned. So we say energy is dropping, our potential energy drops to a lower level. Again, where you set the bar is just arbitrary. I just chose something to show that there was a difference. As everything is burned, we end up with products that have a lower potential energy. So we know that this was an exothermic reaction because we went from top to bottom. So we went from high energy to low energy. We know that energy was released, and we say that the difference between the two bars, signified by this arrow right here, is the delta H value. So for this case, it would be 700, I think, negative 726 kilojoules. So that specifies how much energy was used or released. So here's an example right out of your textbook. On the left side here we have exothermic chemical change. So magnesium and oxygen, so this is an oxidation reaction. We start off at high energy. As the reaction proceeds, energy is being released. So specifically for the formation of magnesium oxide, we have negative 600 kilojoules of energy being released, and our final product is very stable. It's at a low energy. So the difference between these 2 points right here is negative 600 kilojoules. For an endothermic reaction, it's reverse. We start off at low energy. We have to input energy. So we're saying for the decomposition or electrolysis of water, we're inputting 285 kilojoules per mole of water to get our products. So water starts off at a low energy. We have to input energy, and we end up with products that are at a much higher energy level than what we started with. If you look on page 319, page number 319 on your Nelson textbook, there's an example for photosynthesis. It shows information represented all 4 ways, and it also shows the reverse reaction. And something you'll notice is the numbers stay the same. So if you have an exothermic reaction going one way, that's negative 2,000 kilojoules. The reverse reaction will also be 2,000 kilojoules, but it will be a positive. Okay, I would highly recommend that you look at this example, and there are a few practice problems, very good for practice. I think just about number 1 to 5, all of them great for practice for the test on this Friday.